Hey everyone, I hope you're doing well today. In this video, I'm going to cover 10 different practice problems dealing with trigonometry to get you ready for the ACT or the SAT. Feel free to pause the video now if you'd like to try any of the problems first on your own, otherwise I'm going to be going over each of them one by one. I encourage you to grab some paper, something to write with, and let's do some math together. Here's the first problem. If x is between 0 and 90 degrees and tangent of x is going to be equal to 15 over 8, then we need to find out what cosine of x is equal to. Now, since we're told that x is between 0 and 90 degrees, that means that our angle measure has to be in quadrant 1, and all three trig functions are always positive in this location. Okay, so that's a good part to start with. Our angle measure of x degrees is going to be somewhere in this quadrant. Now, another important thing to remember is our good old acronym of SOHCAHTOA. Remember, sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Given that tangent of x is equal to 15 over 8, we can go ahead and use this part of SOHCAHTOA and write the equation that tangent of x degrees, whatever that angle is opposite over adjacent, or 15 over 8. This 15 is going to represent our opposite side of angle x, and 8 is going to represent the adjacent side to angle x. So we only use SOHCAHTOA when we're dealing with right triangles, so we can draw our right triangle over here in quadrant 1, since x has to be between 0 and 90 degrees, and it might look something like this. Our angle measure of x would be located right here, and our opposite side to that has to be 15, and the adjacent side must be 8. To take a closer look at that triangle, I'm just going to redraw it, but a little bit bigger and cleaner off on the side here. So go ahead, something like this. And here is our right angle. X degrees is right over here. It's between 0 and 90. 15 we know is the opposite side, and 8 is the adjacent side. And again, relative to angle x, this 15 is going to be the opposite side length, and 8 is going to be the adjacent side length. Now, since the question is asking us what cosine of x is equal to, we need to use this ratio right over here, which is adjacent over hypotenuse. Now, we already know the adjacent side is going to be 8, that's right over here, that's the adjacent, but we need to figure out how long the hypotenuse is, which is this length right over here. To do so, we can use the Pythagorean theorem, which is a squared plus b squared is equal to c squared. A is going to be 8, which is one of our legs, b is going to be 15, the other leg, and c always represents our hypotenuse, or the diagonal side length. 8 squared is 64, 15 squared, I believe, is 225, and c squared still stays the same. Combining 64 and 225, that should equal, I think, 289. That equals c squared. And taking the square root of both sides, 289 happens to be a perfect square, so I think we should go with c is equal to 17. So that's going to be the hypotenuse of this triangle. So while we were given the information that tangent of x was equal to 15 over 8, which is the opposite over adjacent, we can now say that the cosine of angle x is the adjacent over hypotenuse, or 8 over 17. So we can say that cosine of angle x is equal to 8 over 17. That'll be our answer. Number 2. One angle in a right triangle measures a degrees, such that cosine of that angle is equal to 24 over 25, and we need to figure out the measure of sine of 90 minus whatever angle a is. Now, to solve this problem quickly and efficiently, you're going to want to understand the relationship between this a and 90 minus a. So if you were to take this angle a and add on the other angle of 90 minus a degrees, you can notice here that this positive a and negative a will cancel out, and that this is just equal to 90 degrees. Now, the significance to that is that this a and 90 minus a are what we call complementary angles. All right, so these two things add up to 90 degrees. Now, just say I were to tell you that angle a and angle b are complementary angles. It turns out that if you were ever to take sine of angle a, that's always going to equal cosine of angle b. And if you were to take sine of angle b, that would always equal cosine of angle a. Because the opposite of angle a is always going to be the adjacent for angle b, this always holds true. That being said, this 90 minus a degrees and this cosine of a degrees are complements to each other, which means that sine of one is equal to cosine of the other. Basically, we can just say that sine of this 90 minus a degrees is equal to 24 over 25, the same thing as cosine of a degrees. Now, if how I went over the problem already made sense to you, feel free to skip ahead to the next problem. If, however, you want a little refresher to make sure you understand this concept a little deeper, stick around for this next part. So here is a right triangle. I'll make a separate example and hopefully clarify anything. We know this bottom right angle is 90, and maybe I'll start off with the ratio of 3, 4, and 5, famous Pythagorean triple. Labeling this angle down here as A degrees and this top one as B degrees, we could write the equation as 90 degrees plus A degrees plus the B degrees is equal to 180 degrees. Subtracting 90 degrees from both sides, we could write the equation A degrees plus the B degrees is equal to 90 degrees. And subtracting A degrees from both sides, we can say B degrees is equal to 90 degrees minus A degrees. So the connection I want to make here is that B degrees, which is the angle inside the triangle, is the equivalent to this 90 minus A, which is the same thing as the other angle. It's complement of angle A. Now the original equation here said cosine of A was equal to 24 over 25, so let's just use that as an example. If we have cosine of this angle, that's going to be adjacent over hypotenuse, or 4 over 5, I'll write that here. Cosine of angle A is equal to 4 over 5. And what if we were to take a look at sine of the other angle? Well, if we were to take sine of B degrees, well, sine of B, well, for B, this 4 is actually going to be the opposite, and the hypotenuse actually stays the same. So if we were to take sine of angle B, that's also going to be 4 over 5. Notice how the opposite of one of them is the adjacent for the other. And hopefully that clarifies why both of these would be 24 over 25. Number 3. If tangent of x is equal to 7 over 24, we need to find the value of what sine of x is equal to. Now, before we even get started, I'm just going to write down my ratios of SOHCAHTOA just in case. Helps me kind of just keep everything organized and I don't mess up my ratios and make silly mistakes. And since we're dealing with SOHCAHTOA, we should have some sort of right triangle, right? So I'm going to draw a right triangle, maybe something that looks like this. Close enough. I call this one maybe x degrees on the bottom left. And if we're saying tangent of this angle, tangent is what? Tangent is going to be opposite over adjacent. So the opposite side needs to be a 7. I'll go ahead and write 7. That's the opposite side of x. And the adjacent side is going to be 24. So put that right down here on the horizontal side, okay? So we need to find out what sine of x is equal to. Well, we know that sine is opposite over hypotenuse, right? So if we're looking at this x degrees, what's the opposite? Well, the opposite is this 7, but the hypotenuse, we actually don't know, right? The hypotenuse is right over here. So we're going to have to figure out what this side length is. So I'll label that this is going to be the hypotenuse. And just like an earlier problem, we can use Pythagorean theorem to do this, right? We can say, we know a squared plus b squared is equal to c squared. It doesn't matter what a and b are. Maybe a is 24 and b is 7. When I say it doesn't matter, I mean you can switch which one's a and b. Just don't switch it with c because that's the hypotenuse. I think 24 squared should be 576 and 7 squared should be 49. That's equal to c squared. 576 plus 49, I think that's going to be 625, if I'm right. I think so, 625. That's equal to c squared. And if you then go ahead and take the square root of both sides, 625 is a perfect square, so c should equal 25. Now I know it's a little confusing sometimes to be using different letters, but this c is really our h, or the hypotenuse, right? So we can then go ahead and say that sine of x, sine of angle x, which is going to be the opposite over hypotenuse. Again, the opposite side is going to be 7 from angle x, and the hypotenuse we just figured out is 25. So this is the value of what sine of x is. And while I don't ask for it, if you wanted to find out what cosine of x was equal to, that would just be the adjacent over hypotenuse, and that would be 24 over 25. There's a little extra credit for you. Number 4, in a right triangle, one of the acute angles is cosine of pi over 3, and cosine of pi over 3 is equal to sine over x. We need to find out the measure of angle x in radians. So to get started, I'm just going to sketch a right triangle, and hopefully you're seeing the theme of that since everything with trigonometry right now, with sine, cosine, and tangent, is dealing with a right triangle. And what's interesting about the information they tell us is that cosine of this pi over 3, that's in radians, that's an angle measure, is equal to sine of whatever x is. That's an unknown. Now, I don't know about you, but I understand degrees better than radians, so if you can't remember how to convert radians to degrees, maybe the one thing you can try to memorize is that 2 pi is equal to 360 degrees, right? Just memorize this one thing, because if you take half of 2 pi, that's just pi, and half of 360 would be 180. That's another equivalent that's good to know. Then if you wanted to know what pi over 3 is, you would just divide the pi by 3, and that's literally just pi over 3. Then divide 180 by 3, that would be 60 degrees. So I just like trying to memorize this one ratio, or just remember that 2 pi is equal to 360 degrees, and I can always just use that and convert it down or break it down into smaller ones, and I can always find out what the radians are in degrees. So bringing that back over to the equation, maybe it's easier for us just to write this as cosine of 60 degrees, right? That's the same thing as pi over 3 in radians, and that's going to be equal to sine of what angle measure? Now actually, at this point, if you remember from a couple problems ago, we did one that dealt with complementary angles, right? So if you take cosine of one angle, it's always equivalent to sine of its complement. So the way you can think about this is maybe 60 degrees, which we already know, plus what angle, that's going to be x degrees, is equal to 90 degrees, right? They're going to be complementary to each other. And if we take away 60 from both sides, then we can say that this x degrees must equal 30 degrees. Right? Sine of 30 should equal cosine of 60. So at this point, we can go ahead and say that x equals 30 degrees. Okay? Now, they tell us specifically not to write it in degrees. They say to write it in radians. So if you needed to do that, then maybe if we go back over to my little chart over here, if we were to divide this by 2 to get 30 degrees, then what's half of pi over 3? Well, half of a third is a sixth. So pi over 6 is equal to 30 degrees. We can go ahead and snag that and say that x is equal to pi over 6. And in radians, that would be this angle measure. Now, if you wanted to go back to the triangle, that means that this angle here would be 30 degrees, and this angle is 60 degrees. And if it's a 30, 60, 90, hopefully this rings a bell that this would be 1 to 2 to root 3. This is one of your special 30, 60, 90 triangles. And if you were to take cosine of 60 degrees, cosine is going to be adjacent over hypotenuse. We can say that cosine of 60, I'll go ahead and write it down over here, cosine of 60 degrees is equal to 1/2. And if we were to take sine of this angle measure, that's going to be opposite over hypotenuse. So we can say that sine of 30 degrees, or its complement, is also equal to 1/2. And there you have it. Since pi over 3, which is 60 degrees, plus pi over 6, which is 30 degrees, equals pi over 2, then we know that sine of one of them is going to equal cosine of the other. Number 5, if the area of triangle ABC is 225 and side AB is equal to 17, go ahead and label that. The question is, what is the value of cosine of x? Now, it's important to know right off the bat that this is not a right triangle, right? So if it's not a right triangle, that means we can't use SOHCAHTOA. Now, while you might think of maybe using the law of sines or law of cosines, I wouldn't jump right to that conclusion just yet. Because they told us the area of a triangle, we should maybe think about what that formula is. So area is equal to 1/2 base times height, or you can say base times height over 2, either one's okay. And we already know the base of this triangle, which is equal to 30. Substituting in the 225 that we already know for the area, we can say that 225 is equal to 1/2 times the base, which is 30, times the height. Taking 1/2 of 30, we can go ahead and say that 225 is equal to 15 times h. And going ahead and dividing both sides by 15, we can say that h is going to equal 15, or the height of the triangle is equal to 15. I'm just going to go ahead and label that on the triangle and say that this is going to be 15. Now that we have the height of this triangle, it's really important to know that we actually have a right triangle at this point. Now going ahead and drawing a little bit cleaner diagram over here on the bottom, I'm just going to have a right triangle, maybe something like that. And we know that 15 is the height of it. We already found that out. We know x degrees is going to be on this bottom left angle measure. And remember, this side over here is equal to 17. Now relative to this angle measure x, we have the opposite and hypotenuse, so taking sine would be no problem. But in order for us to take cosine of x, we need to find out the adjacent side length, which is right down here. Now to use the Pythagorean theorem, I'm just going to go ahead and maybe call this side a for now. And I'm going to write that if we take a squared plus b squared that'll equal c squared. So a, we don't know, we're going to try to solve for that. B is going to be 15, one of the legs, 15 squared, is equal to c, which we know is the hypotenuse, is 17. So a squared is going to stay the same. 15 squared is 225, and 17 squared, I believe, is 289. Subtracting 225 from both sides, we'll get a squared is equal to, I think that's 64, that should be right. And then taking the square root of both sides, a is going to equal 8. So filling in that missing piece, we now have the adjacent side to angle x. So again, this relative to angle x was the opposite side. This 17 is representing the hypotenuse, and this 8 represents the adjacent side. So we needed to use the Pythagorean theorem to find out the adjacent side of 8. Now, remembering from SOHCAHTOA, the c part is the adjacent over hypotenuse, so we can go ahead and say that cosine of x is going to equal the adjacent over hypotenuse, or 8 in this case, which we found, over 17. This will be our answer for this problem. Number 6, if the hypotenuse of a triangle has a shown length of 24 units, what is the area in square units of the triangle? So right away, looking at this pi over 3, if that's intimidating, we would just want to remember that that's equal to 60 degrees. And to remind you how to derive that, if you just memorize that 2 pi is equal to 360 degrees, then 1 pi should be half of that, which is 180. And if you want to know what a third of that is, or divide pi by 3, that'll equal 60 degrees. Now if we know that the top right angle is 60 degrees, then this bottom left one should be 30 degrees. And in radians, we can just write that as pi over 6. Because they're asking us to find the area of this triangle, recall that the area of a triangle is going to be 1/2 times the base times the height. And unfortunately, we don't know the base and we also don't know the height. This is a bit of an issue. Now the key to solving this problem is understanding how to use the 30, 60, 90 triangle. So all 30, 60, 90 triangles out there have a ratio of side lengths, right? So if this bottom one's 30 and this top one's 60, this works for all 30, 60, 90 triangles. They always have the ratio of side lengths where the shortest one is always 1. The hypotenuse is always double whatever the shortest one is. And the second leg is always going to be the shortest leg times the square root of 3. So for example, if I took another 30, 60, 90 triangle, and I just drew that right down here, if I told you that was 30, 60, 90, then if this side was 5, then the hypotenuse must be 10, and the other leg must be 5 root 3. So hopefully that kind of clarifies the relationship between the 3 side lengths of any 30, 60, 90 triangle. Now that I hopefully clarified that for you, we should be able to take this 24 and say that this leg over here is going to be 12, right? So if we knew that this is 2 and this is going to be half of it, or this is 10 and 5 is half of it, then we can go ahead and say that half of 24 is going to be 12. And the significance is that actually represents the height of the triangle. The height we now know is 12. How do we use this leg of 12 to figure out this other leg? Well, it turns out it's just going to be equal to 12 root 3, right? So how do we get from this leg to this leg? Well, you just multiply it. You just multiply by the square root of 3. And the same thing, how do we get from this leg to this bottom leg? You just multiply it by the square root of 3. That being said, we just identified that the base is equal to 12 root 3. Substituting these values in, we can say that the area is equal to 1/2 times 12 root 3, or the base of this triangle, times 12, or the height of the triangle. 1/2 of 12 root 3, well, that's just going to be equal to 6 root 3, and we still have to multiply that by 12. And 6 root 3 times 12, just multiply the whole numbers together, 6 times 12, that's going to equal 72, so we'll have 72 root 3 units squared. The exact answer for this problem would be 72 root 3. Now, if you need to get a decimal, go ahead and plug it into a calculator, but otherwise, this would be the exact answer. Now, when we started this problem, the issue was the fact that we didn't know either base or the height. It made it a little bit more challenging. But the key takeaway here is to make sure you know that your 30, 60, 90 triangles have this specific ratio, and while you're brushing up on that, it might be good to brush up on your 45, 45, 90 triangles as well. And once you understand that ratio, you can actually take that 24, take half of it to get the height, and multiply the height by root 3 to get the base, right? So keep in mind that all 30, 60, 90 triangles have this ratio, and all 45, 45, 90 triangles have their own special ratio. Those are good to know for the SAT and the ACT. Number 7, we have if sine of theta, just some angle measure, it could be x for all we care, is equal to 4/5, and we know that this angle measure is between pi over 2 and pi, we need to find out what tangent of theta is, tangent of this angle measure. So just taking a look at this part over here, let's just try to see what that actually means, right? So again, radians are a little bit confusing to understand sometimes. So if we, again, remember that 360 degrees is equal to 2 pi, then dividing it by 2, we know 180 degrees is also equal to pi. And taking half of that, we know that 90 degrees is equal to pi over 2. So I think having this information will help us with what we are actually given, because they give us pi over 2 and pi, and now we know that pi over 2 is just 90 degrees and pi is 180 degrees. Now that we know what pi over 2 and pi really represent, we can just rewrite this and say that 90 degrees is less than theta, which is less than 180 degrees. And the significance of this is that we now know that our angle measure of theta is located in quadrant 2. Drawing a quick coordinate plane just to give you some reference, if I draw our x-axis and our y-axis, 0 degrees would be located here, 90 degrees is here, 180 and 270. So theta must be somewhere in this region over here. It's also important to remind you of our acronym ASTC, or All Students Take Calculus, if you haven't heard it before. The A here just represents that all three trig functions have positive ratios in quadrant 1. The S in quadrant 2 lets us know that sine is the only trig function that has positive ratios. Tangent is the only one with positive ratios in quadrant 3. And in quadrant 4, cosine is the only function that has positive ratios. Knowing that theta, or our angle measure, is in quadrant 2, we know that the value of tangent of theta must be a negative ratio, or a negative value. Drawing a reference angle and a right triangle in quadrant 2, it might look something like this. I'm just going to redraw it a little bit larger on the side. This angle is 90 degrees. Our angle measure of theta is right down here. We know that sine of theta is equal to 4 over 5, and from our SOHCAHTOA, we know that sine is equal to opposite over hypotenuse. We can then label that 4 is the opposite side, and 5 is the hypotenuse. When we have two sides of a right triangle, we can always solve for the last side by using the Pythagorean theorem. Maybe I'll call this side A. And we can say that a squared plus b squared is equal to c squared. Now I know it's a Pythagorean triple, but I'm just going to write it out just in case. A squared plus 4 squared is equal to 5 squared. A squared plus 16 is equal to 25. Subtracting 16 from both sides, we can say a squared is equal to 9. And taking the square root of both sides, we can then verify that a does equal 3. Labeling that right on the bottom, we can now say if we're taking tangent of x, because I think that's what we were originally looking for, tangent of x, well, tangent of this angle measure here is going to be equal to opposite over adjacent, and I can label that one more time. Now we know from SOHCAHTOA that tangent is equal to opposite over adjacent. We can say that tangent of theta should be something like this 4 over 3, opposite over adjacent. Now, before you quickly accidentally say this is the final answer, keep in mind that we are indeed over in this quadrant 2, and only sine gets to be positive in quadrant 2. That being said, we're really close to the answer. Just make sure you throw a negative on there and say that this opposite over adjacent, or tangent of theta, is equal to negative 4/3. Number 8, we need to find out the exact value of what cosine of pi over 12 is, given that pi over 12 is the same thing as pi over 3 minus pi over 4. And we're given this long, crazy looking formula, and we must have to use that in some way. So this long, scary looking formula here, you don't really need to know where it comes from, but you just need to know how to plug things into it. If you're curious, you can look it up. It's the angle sum formula. It helps you solve some trig problems with non-30, 60, 90, or non-45, 45, 90 types of angles. So you can just take it for what it is, and we're just going to try to plug things into it to make this work. Now, while I know they tell us this is true, but if you want to just have some clarification on that, we know pi over 12. If we rewrite this pi over 3 with a common denominator with pi over 4, you can multiply pi over 3 times 4 over 4. So that's going to be 4 pi over 12. and multiplying pi over 4 times 3 and 3 top and bottom, that's going to be subtracting 3 pi over 12. So if you were to take this 4 pi over 12 minus 3 pi over 12, hopefully that makes sense that that is a true statement, okay? And if it helps you to think about this in degrees, feel free to do so. Pi over 3, or 4 pi over 12, is the same thing as 60 degrees, and pi over 4 is the same thing as 45 degrees. I just memorized that from my 45, 45, 90 triangle. So that means 60 degrees minus 45 degrees, that just means that this pi over 12 really just represents 15 degrees. So they're trying to give us a pretty scary looking problem, but hopefully I can help you make more sense of it and make it look a little bit less scary. So we can say that cosine of pi over 12 is the same thing as cosine of pi over 3 minus pi over 4, right? We already said that pi over 12 is the same thing as 15 degrees, and pi over 3 minus pi over 4 is also 15 degrees. 60 minus 45 is equal to 15. Now they give us a bunch of these x's and y's throughout the problem, and they're just basically saying, let's replace each of these values. So this would have to be our x, and this would have to be our y. Now I'm assuming that you're probably also more comfortable working in degrees. I think radians are sometimes a little harder to understand when you're just getting started. So I'm just going to turn everything here into degrees so that it's easier to follow along. Okay, so going ahead, we can say really that x is going to be the 60 degrees and y is going to be represented by 45 degrees. Now that we've established that x is going to represent 60 degrees and y is going to represent 45 degrees, let's write an equation out. Plugging into this formula, we can go ahead and write cosine of 60 degrees minus 45 degrees, which is really just pi over 3 minus pi over 4, or pi over 12, or 15 degrees. That's going to equal cosine of 60 degrees times cosine of 45 degrees. And I'm just going to go ahead and get rid of this because it's in the way, plus sine of 60 degrees times sine of 45 degrees. Now when we have this cosine of 60 degrees and sine of 60 degrees, we want to remember our 30, 60, 90 triangle, right? So if I were to draw that special right triangle that has a ratio that always works for all 30, 60, 90 triangles, we have our 60 degrees here, 30 degrees, then the opposite of the 30 degrees is always the shortest, the hypotenuse is always 2, and this is the square root of 3. Then we can go ahead and say that cosine of 60 degrees, which is adjacent over hypotenuse, that's just going to equal 1 over 2. Substituting that in here, we can say that this is going to be 1/2. That's what cosine of 60 is equal to. Now for sine of 60, here's our 60 degrees. That's going to be opposite over hypotenuse, or O over H. Root 3 is our opposite, and 2 is our hypotenuse. We can then go ahead and say that sine of 60 degrees is going to equal root 3 over 2. Now for dealing with the trig functions that have the 45 degrees. So we can't use this triangle of 30, 60, 90 because it doesn't have a 45 degree angle. Instead, we can use our other special right triangle, the 45, 45, 90 triangle. Let's draw that right down here. So we know this is an isosceles triangle, right? 2 of the angles are the same, so 2 of the sides are the same. And the ratio is going to be 1 to 1, they have to be the same. And the hypotenuse is always just going to be a side length times root 2. Now taking cosine of 45 degrees, that's adjacent over hypotenuse, or 1 over root 2. I can go ahead and write that here as 1 over root 2. And sine of 45 degrees is going to be opposite over hypotenuse, which is the same thing, and we can also write 1 over root 2. Now you might remember that we shouldn't really have any radicals in the denominator, so when we have this 1 over root 2, keep in mind that if we're going to rationalize it, we can just multiply the top and bottom by the square root of 2 over 2, and that would just equal root 2 over 2, and that's the same thing. So I'm just going to go ahead and swap this out so that it's easier to use and you don't have to do it later, and we don't have any irrational denominators, so root 2 over 2. So now that we don't have any trig functions, this is going to be a little bit easier to work with. We're multiplying these two fractions together, and we're adding the product of these two fractions over here. Multiplying this 1/2 by root 2 over 2, that's just going to get us a root 2 over 4. And multiplying this root 3 over 2 by this root 2 over 2, that's going to give us the square root of 6 over 4. This right here is what cosine of pi over 12, or cosine of 15 degrees is equal to. So just to recap real quick, it's important to recognize that pi over 3 and pi over 4 are 60 degrees and 45 degrees, which lets us use our special right triangles. While this formula we're given looks pretty intimidating, we really just needed to plug in those values of 60 degrees and 45 degrees into a bunch of spots. Using your typical SOHCAHTOA for these two special right triangles, we were then able to find out these ratios. After rationalizing the denominator, we could then multiply and just follow the order of operations, multiply these two fractions together, and we end up getting root 2 over 4 and root 6 over 4. And be careful not to actually combine these since they don't have the same radical, okay? And we just write our final answer of root 2 plus root 6 over 4. Here's number 9. If sine of A is equal to cosine of C, we need to find out what sine of ABD is minus cosine of DBC. And we don't have any numbers. Great. Now there must be something that we can figure out even though they're not explicitly telling us. So actually take a look at this statement here. This is actually pretty important. So if you recall from earlier that if we take sine of one angle and if it equals cosine of the other and the kind of the opposites and adjacents swap, remember those things about complementary angles? Then that means that angle A plus angle C equals 90 degrees, right? They have to be complements to each other. Taking that one step further, we know that angle A plus angle B plus angle C should equal 180 degrees since they're three angles of a triangle. Given that we already know that angle A plus C equals 90 degrees, swapping these two out, we can say that angle B plus 90 degrees is equal to 180 degrees. Subtracting 90 degrees from both sides, we can then say that angle B is equal to 90 degrees. Now the reason this is so important that we found is because now we know this is a right triangle. Now this angle of ABD is this angle here from A to B and then B to D, so that's this angle measure. And angle measure DBC is located here, so from D, that's right on top, B, and then C. So that's this angle measure here. Since angle ABD and angle DBC are right next to each other, and they make up this angle B, we can go ahead and say that angle ABD plus angle DBC is equal to 90 degrees, right? It's a right angle. And that means those are also complementary angles, right? So this is like showing up all over the place here. And so the really important takeaway here is that whenever you have two angles, just say angle X and angle Y are complementary to each other, they add up to 90 degrees, you can always say that sine of one of them, right, sine of X degrees, is going to equal cosine of Y degrees. That's always going to be true as long as they're complementary angles. Bringing that back to this problem, we can say that sine of this angle ABD must be actually equal to cosine of angle DBC. If sine of ABD is equal to cosine of DBC, then subtracting them means that they must actually equal 0. So while this is a pretty tricky question because we're not actually given any angle measures, it's important to notice here that we have sine of A is equal to cosine of C. The only time that can possibly be true is if angle A and angle C are complementary. Okay, that's really important to remember. From that, we were also able to find out that this angle B was also equal to 90 degrees and that this was a right triangle. Then once we were able to figure out that angle ABD and angle DBC added up to angle B, or 90 degrees, that meant that they were also complementary angles. Sine of one of those angles is equal to cosine of the other, so subtracting them, we must get 0. Number 10, the final question of this video. If sine of x is equal to cosine of 13 pi over 6, and we know that x is between 0 and pi over 2, we need to find the value of x. Now, just something I'm noticing with this problem that's come up with a bunch of other ones is that if we take sine of angle A, and if that's equal to cosine of another angle, I'll just call that B, that means that A and B have to be complementary, right? That's come up a bunch of times here, so hopefully that's something that you're catching on to, because that's a nice relationship to just kind of know and keep in your back pocket for different trig problems. Now, I don't necessarily know if we are going to use that particular aspect in this problem, but it's just something I recognized from the beginning. Now when they tell us that x is between 0 and pi over 2, let's also try to remember that 0, well that's just going to be 0 degrees, and pi over 2, that's equal to 90 degrees. So just for some reference, if we are taking a look at this on a coordinate plane, and we have our x-axis and our y-axis, then 0 degrees is located here, 90 degrees is up top, and our angle measure of x has to be somewhere in this region in quadrant 1. So I just want to make that very clear from the start. Now, while we can't really work with the sine of x right now, we can work with this cosine of 13 pi over 6. So let's just try to understand what 13 pi over 6 is to begin with. Well, for starters, we know that 360 degrees is equivalent to 2 pi. Now I'm going to take this 13 pi over 6 and break it down into two smaller pieces. I'm going to break it into 12 pi over 6 plus a single pi over 6. And the reason why I'm doing that is just to illustrate to you that this 12 pi over 6 right here is the same thing as 2 pi. Rewriting this into something that even makes more sense, we can say that this is going to be 360 degrees plus, what's pi over 6? Pi over 6 is just equal to 30 degrees, right? So this is just equal to 390 degrees. Now at this point, it's important to remind you that when we're drawing an angle, we start on the horizontal positive x-axis and we move counterclockwise. So if we were to move a full 360 degrees, we would be back at 0, and move another 30 degrees, we would actually end up somewhere right over here, right? 30 degrees away from the horizontal x-axis. That being said, it should make a little bit more sense for us to not actually consider this 13 pi over 6 as 13 pi over 6, but we can actually subtract the 2 pi, or take away 360 degrees, since we're going to get the same angle, or the same location rather, and that's going to equal pi over 6. We're basically just taking away one revolution around the circle to let us know that 13 pi over 6 and pi over 6 are in the same location. Thinking about this in degrees, we can say that 390 degrees, instead of going around a full circle and taking away the 360 degrees, that this is just equal to 30 degrees. Instead of going around 360 degrees plus another extra 30 degrees, we can just say, let's just move 30 degrees and we'll be at the same location. Now that we know that 13 pi over 6 and pi over 6 are in the same location, instead of saying cosine of 13 pi over 6, let's just think about this as cosine of pi over 6. That'll get us the same answer. Pi over 6 is 30 degrees, so if we take a look at this triangle that we can form on our coordinate plane, then if I draw this off on the side, over here, maybe something like this, looks pretty good. Okay, then this has to be 30 degrees, or pi over 6. Again, I'm just going to keep everything in degrees if I can. This must be 60 degrees. And since this is a 30, 60, 90 triangle, this is going to be 1 to 2 to root 3. Again, that's our ratios for our special right triangle. And cosine of this 30 degrees is going to be equal to adjacent over hypotenuse. So we can say that cosine of 30 degrees, or cosine of pi over 6, or maybe I'll just go back to the original and just write cosine of 13 pi over 6 so it's more clear, that is equal to root 3 over 2. Now since we're looking for the value of x, and we know that sine of x is equal to the same thing, sine of what angle is also going to get us root 3 over 2? Well, it turns out that sine of this 60 degrees over here is going to equal the opposite over hypotenuse, which does match the root 3 over 2. So we can go ahead and write that sine of 60 degrees, and what's that in radians? Well, in radians, that should be pi over 3. Okay, same thing as 60 degrees, and that'll also equal root 3 over 2. Showing you all the steps here, we can say that angle x is equal to pi over 3, or 60 degrees, depending on which form you're looking for, whether radians or degrees. While I tried to go through a very thorough explanation of this, it's important to also just notice from the beginning that this 13 pi over 6 is in quadrant 1 and is the same location as 30 degrees. And what's the complement of 30 degrees? Well, the complement of 30 would be 60. So from the very beginning, we would know that if A and B were complementary, right, then sine of this angle has to equal cosine of this angle. And if 13 pi over 6 is the same location as 30 degrees, then its complement must be 60 degrees. And that wraps up this video on 10 different practice problems dealing with trigonometry to help you get ready for the ACT or the SAT. If you found this video helpful in any way, I'd really appreciate it if you could give it a thumbs up and maybe even leave a comment. If you're taking the ACT or SAT soon, I wish you the best of luck and I know you're going to do great. If you'd like me to make a video on any other particular topics, let me know in the comment section down below and I'll definitely try to work on it. As always, keep up the great work and I'll see you in the next one.